Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders, year 2010, problem number 1. Let S be the sum of the invertible elements of a finite unital ring A. We wish to prove that either S squared is 0 or S squared is S. So here are my hints for this problem. First, consider the case when 1 plus 1 is not 0. And in this case, note that, of course, A is invertible if and only if minus A is invertible. And moreover, A is not equal to minus A. So you can pair elements, invertible elements together, and they cancel each other out because one is the opposite of the other one. But when 1 plus 1 is 0 in our ring, enumerate the set of invertible elements a1, a2, up to an, and justify that for any k, ak times s equals s. And finally, note that s squared can be written in this form, and that should be enough to finish this problem. So give this problem a try, and I will see you in just a minute. Alright, so let's consider first case, case number 1. Case number 1, when 1 plus 1 is not equal 0 in our ring. In our ring A. Notice two observations. First of all, for every element A of our ring, A is invertible if and only if minus A is invertible. Pretty easy to see that. And moreover, for every element A of our ring, invertible element, A is not equal to minus A. Why is that? Well, because you can take inverse on both sides and you will get that 1 is not equal minus 1, which is true because 1 plus 1 is not 0. Well, that means this implies that A inverse has units of A has an even number of elements. Even number of elements, and moreover, S is just 0 because we are pairing A with minus A. So S squared equals 0 as well. So this was rather easy. Second case, much more interesting. Case number 2 will be when 1 plus 1 equals 0 in our ring. In our ring A. Now, notice the following. S squared, and maybe, you know what, let's enumerate before we do it. Let the set of invertible elements of A be A1, A2, AN. Let's enumerate them. Now, S squared equals S times A1 plus A2 plus AN, which can be written as SA1, SA2, and so on up to SAN. Now, I claim that this equals S for every element. Maybe let's write it. Claim. My claim is that for every k from 1 to n, SAK equals just S. Let's prove this claim. Proof. Consider the following. Let k be a number from 1 to n, and let's consider the following mapping. I will denote it by psi. Psi takes an invertible element, aj, let's say, and returns aj ak. Notice that, well, first of all, it's properly given. If we multiply two invertible elements, we are once again in the set of invertible elements. And moreover, this function is injective. Psi is injective. Because, well, why is that? Because if psi of ai equals psi of aj, this is equivalent to saying that ak equals ajak, and after taking ak inverse on both sides, we get ai equals aj. Also, remember that this set is finite, which means that psi is bijective. Well-known property. Every injective function from a finite set into itself is also bijective. So, if you think about it, this in turn implies that sak, which is a1 plus a2 and so on, plus an ak, it's a1 ak plus a2 ak and so on, an ak. If you think about it, every invertible element appears exactly once in this list. They are just in different order, but the order of summation does not really matter because it's commutative. Yes, so it's psi of a1 we can write, plus psi of a2, psi of an, which is exactly a1, a2, plus an, which is s. Just summed in different order, which proves my claim. And now our problem becomes very easy, because s squared, as we have noticed, it's sa1 plus sa2 and so on plus san. Every element is just s, so it's s plus s plus s n times. So it's n times, or maybe let's write it like that, because we know that 1 plus 1 is 0, so it's either 0 or s. 0 if n is even, and it's n when it is not. Why is that? Well, because here we will use the fact that 1 plus 1 is 0 in our ring. It's 0 in our ring. So it's exactly what we wanted, because s squared is either 0 or s, and in the first case it was always 0, which concludes the proof. And that closes our problem. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.